College of Engineering. Today I'm going to be talking about deterministic finite automata. Automata is a mathematical model used to represent a system that processes a given input and transmission from one state to another based on the input. Definition and components of DFA. Deterministic behavior. The DFA has a deterministic transmission function, meaning that for each state and input symbol, the machine can only transition to one state. Components. The components of a DFA include a finite set of states, a finite set of input symbols, a transmission function, and a start state, and a set of accepting states, distinct states. Each state in a DFA must have a unique transition from each symbol in the alphabet. This distinction leads to its deterministic nature. Transition function and its diagram. Transition function in DFA, the transition function determines the next state when a specific input is provided. State diagram. The state diagram visually represents the transition between states based on the input symbols. It provides a clear visualization of the DFA behavior. Directed arrows. The state transition are often illustrated with directed arrows showing the movement from one state to another when a certain input is received. Accepting states and language recognition. Accepting state. These states in the DFA where the machine halts, signifying that the input provided belongs to the language recognized by the DFA. Recognition process. The language recognition process involves feeding the input to the DFA and observing whether it ends in the accepting state. If it does, the input is recognized. False recognition. If the DFA ends in a non-accepting state, the input is not a part of the language recognized by the automation. Equivalence of DFAs and regular language. Mathematical proof. The equivalence of DFAs and regular languages is given by showing that for every DFA, there exists a regular language and vice versa. Fundamental concept. The regular language can be recognized by DFA, making them equivalents in terms of excessive power. Practical application. The understanding of this equivalence is essential in various areas of the computer science, particularly in compiler design and formal language theory. Determinization of NFA to DFA. Non-deterministic nature. NFA represents non-deterministic behavior, where there could be multiple transitions for a given input in a particular state. Deterministic transformation. Determinization is a process of converting an NFA to an equivalence DFA, ensuring the elimination of non-deterministic behavior. Subset recognition. The determinization of an NFA involves constructing the DFA that represents the same language as the original NFA throughout the use of specific algorithms. Minimization of DFAs. Optimizing states. The goal of DFA minimization is to reduce the number of states while preserving the language recognized by the automation. Equivalent states, states that can be combined without affecting the language of recognition, are identified and merged during the minimization process. Final minimized DFA. The result is a minimized DFA with the least number of states possible, maintaining the same language recognition capabilities as the original automation. Automata theory application in AI. Pattern recognition. The DFA concepts are utilized in AI algorithms for pattern and sequence recognition, enabling machines to understand and interpret complex data. Language processing. The natural language processing systems incorporate DFA symbols principles to analyze and interpret human language, facilitating effective communication with machines. Algorithm optimization. Efficient algorithm based on automata theory form the foundation of optimizing various AI processes, contributing to improve performance, resource utilization. DFA implementation in software development. Lexical analysis. Compilers and interpreters use DFA to perform lexical analysis, recognizing and tokenizing the source code for efficient processing. String matching. String matching algorithms utilize the principles of DFA to search a specific pattern within the text and data, providing valuable functionalities in various software applications. Data validation. DFAs are employed in data validation to define and enforce specific rules and patterns, ensuring the accuracy, integrity of input in the software systems. Challenges and advances in automata theory. Complex language behavior. The study of automata theory continues to address complex language recognition challenges such as non-regular languages and advanced grammatical problems. Quantum automata. The exploration of quantum finite automata represent integrating opportunities for expanding the computational power, expressive capabilities of automata-based system. Blockchain applications. The development of blockchain algorithms and smart contracts involve leveraging automata theory concepts to enhance security, decentralized, conscious mechanism.